We're entering day 2 of this journey. And today we're going to introduce the thing that we will actually be talking about forever. We're going to start talking about series. Now, I intentionally avoided this word yesterday. I never said the word series. The word we were using yesterday was sequences. And there's a huge difference between the two, and you have to keep them separate in your head. Sequences in your brains were just what? Patterns of numbers. Just going from number to number to number to number. Series is what we're dealing with up here. A series is this thing. A series is the summation of a sequence. And most of you have seen this symbol before, hopefully in pre-cal or somewhere else. This symbol is the summation sign. It means I'm going to sum up a bunch of things. But we have to figure out what all the accoutrement is. Accoutrement means extra stuff on the side.
So like a toothpick French. Like the garnish and nachos.
Yeah, actually. Yeah.
What is it?
Accoutrement. This thing on bottom. This thing tells me the starting in value. Unlike sequences, these can start wherever. I could start it at 0. I could start it at 1. I could start it at 2. Sequences, I could, but they'd be really weird. Sequences always started at n equals 1. These could be anything. N equals 0, 1, 2. Usually, I start them at 0, 1, or 2. Most of the time, you won't see anything other than that. But you have to pay attention on where it's starting. The top number, what do you think that represents? Right, how many I go out to. The ending in value. And then the thing inside is what I'm actually using to find my pattern. This is my sequence. So the actual definition of your series is just the summation of a sequence. Series is the summation of a sequence. Let's do some examples and expand it out real quick before we start getting into actual hard calculus. If I gave you summation n equals 1 to infinity, or sorry, not infinity. Let's go 4 of x squared. What value is it starting at?
1.
Where is it ending?
4.
4, and this is the pattern that I will use. So the first one is going to be 1 squared, which is 1, plus, bless you, 2 squared, which is 4, plus 9, plus 16. Right, and then I stopped there. So I started at n equals 1, ended at n equals 4. 16, 4, 20, 1, 9, 10, 20, 10 is 30. Cool?
Cool.
That's what a series is. It's just the summation of all of the sequence that I'm going through. Where we are going to start getting into this, and where this calculus actually meets what we're doing, are infinite series. infinite series, if you had to guess, what is an infinite series? It keeps on going. Goes to infinity. Now, this is going to be, again, I just have to convince you of this fact up front, that infinite series, even though I'm adding up infinite numbers, many of these will actually sum up to a number, which is weird. I'm saying I'm going to add up infinite numbers, but it's going to equal like 5 or 6 or something like that.
You're just adding like a specific thing in the series?
Right, and let me show you an example of this. Let's look at the summation from n equals 1 to infinity of 1/2 to the n. This is an example, and I'm going to show you pictorially what this is to hopefully try and get this in your head of why this is and what this looks like. Cool? If I were expanding this out, this is 1/2 to the first power, which is just 1/2, 1/2 to the second power, which is 1/4, plus 1/8, plus 1/16, plus 1/32, and on and on and on and on. Now, let's look at it as in terms of area. Let me see if I can convince you of that. I'm going to make a 1-by-1 block. Alright, the first business I have is 1/2, right? So I'm going to split this. Jacob, stop. The first thing I'm going to do is split this down the middle. This entire thing represents a half of the block. With me? Then I'm going to add a 1/4. So I'm going to add 1/4 of that block, which means the remaining stuff, split it right here. This is 1/4 of the block. Cool? So it takes care of that. Let's add 1/8 of it. So that means take the rest of the remaining 1/4, split it in half. That's 1/8. Let's add a 16th. That's going to be this part right here. I can split the remaining 16th in half again. That's going to be 1/32. And I keep on adding smaller and smaller bits. Now, technically, will I ever fill in this little area right here?
No.
I'm going to keep on getting smaller, smaller. In other words, I'm like filling a basket with big rocks, and then small rocks to fill in the space in between, and then even smaller rocks, and then sand, and then silt, and I'm filling it smaller and smaller and smaller. But I'm going to get really close to it. How long is this side over here?
1.
How long is this side over here?
1.
This is equal to 1. All of this, if I keep on adding it, is going to be equal to 1.
I know the size.
Would it be squiggly lines?
Nope, it is actually equal to 1.
Exactly.
Or is it like 0.99?
Nope, it actually equals 1.
Is it because it goes to infinity?
Because it goes to infinity, right. And this is an important question. Hey, side conversations, hush. The reason it's actually equal to 1 is because it goes to infinity. If it stopped anywhere before infinity, then that would be 0.9999999. But because it actually goes to infinity, we're saying theoretically, I go all the way out, this is actually equal to 1. Dig? Alright. So, we are going to look at 3 cases with this. First case, which we just encountered, is it converges. if something converges, just like with our other sequence, with our sequences, the series, if the series converges, it means that I add up to a number. Like 5, 6, -3, 0. It doesn't matter what the number is. As long as it reaches a number, we call that converging. So it adds up to a finite number. Second case, we have converging. What else do you think we have? Diverging. It diverges. Now, that doesn't necessarily mean it equals infinity. That's not the only case. It just means that it does not sum up or add up to a finite number. Most of the time, you'll encounter things that go to infinity. But other times you can have other cases, just like with our sequences. What was another case in which a sequence did not converge but didn't actually go to infinity? Oscillating. For example, I'll give you a real quick one. Summation n equals 1 to infinity of -1 to the n. That's equal to, if I plug a 1 in there, that's -1. I plug a 2 in there, -1 squared would be 1, so -1 plus 1, minus 1, plus 1, minus 1, and that continues on forever. So my sum is going from -1 to 0, -1 to 0. It's oscillating. It's going in between two things. It reaches those two things, but it never settles down on one thing. It just keeps going back and forth between them. Cool?
If it's infinity.
If it goes to infinity. If I had said like 12, that would be fine.
Then it'd be either 0 or -1.
Correct. But what we're going to deal with, we're only going to deal with infinite series. Say it again. Diverges.
So there's no like equals.
Right. And most of the time we'll get in that in just a minute. Most of the time we're not actually trying to find out what they equal. We're just trying to see if they equal something. The last case is if they are conditionally convergent. Conditionally convergent won't come up in the next couple days. It will pop up mid next week. I'm just introducing it now so you have that bouncing around in your head. Conditionally convergent means that the sum from n equals a number to infinity of my regular sequence converges, but the summation the absolute value of that thing diverges. That's what conditionally convergent means. Is normally if I just look at the function and the sequence that's in there and I add up all the numbers, great, that converges. But the moment I slap absolute value bars on it, it starts diverging. That's what we call conditionally convergent. It means it converges sometimes, not all the time. Cool? Yes, ma'am. You only have to check for that if I specifically state, is it conditionally convergent? All the other times, you're literally just seeing, does it converge or diverge? You don't have enough knowledge for it to make sense yet. Next week. Alright, real quick, 20 seconds. Turn to a neighbor and tell them what converging, diverging, and conditionally means in terms of series in your own words. 3, 2, 1, go.
I mean, it worked.
Like a way?
Wait, you're going out. He's so bad.
What? Why is everyone asking me this today? No, I don't. I mean, I do. I don't use it.
What? Norvik said only one.
Wow.
Yes, I do.
So I'm taking a survey of people throughout the day.
Wow. Alright. We're going to introduce the first gift of Christmas. The first tool, and no, I'm not referring to Leo. I know. It's just a joke. The first tool. When going through these, calm children. When going through these, eventually, I'm going to give you like 10 series, and I'm going to need you to be able to identify. Hey, shh, stop talking so I can teach. I'm going to need you to be able to identify what type of series it is. Therefore, you can tell me if it converges or diverges. We're going to introduce the first series test. It is something you actually know, or somewhat of it. The geometric series test. This follows your knowledge of what you sort of know geometric means. We know geometric sequences are things that I do what to get to the next number. Alright, so all of these are going to be things that I multiply or divide to get to the next number. The pattern that they follow is the summation starting at n equals a number out to infinity of some ratio raised to the n exponent, where the ratio is going to be a constant and the exponent will be a variable. It's important to know which is which, because in a couple days I'm going to teach you another test that flips those, that says I have a variable raised to a constant exponent, and we have a certain test that we do for that one that is a little bit different. But right now we're looking at a constant raised to a variable exponent, like 1/2 to the x, or 2 to the x. We're going to use n's, not x's. You could also see it like this. There's a couple different ways you could see them. I could have the summation, again, n equals a number to infinity, but I could have a number up here. Usually that represents the first term. So if I have like a 5 up there, that would be the first term. You have to be careful, though. That depends on this counter. You just want to list out the sequences so you can actually see what it is. This is the same format. Or I could also have a format like this, which is summation starting at some number, going to infinity, same business, but that exponent doesn't just have to be an n. It could be something like an n minus 1, or plus 1, or plus 5. It really doesn't matter. It's just something raised to some variable exponent with a number downstairs. Now, again, we're trying to see, the whole business is we're trying to see if they converge or diverge. Luckily, with all of these tests, there's going to be a really nice condition that tells us if it converges or diverges. In this case, if the ratio, the absolute value of the ratio, don't care about the actual positive or negative, is less than 1. In your brain, that's a fraction. And yesterday we sort of talked about this. If the fraction, the bottom was bigger, what happened to the sequence? That also happens to the series. Just with this type of series, though. So if a geometric series has a ratio that is less than 1, it converges. If it converges, and this goes to Claire's question a while ago, this is one of the only ones that I can actually figure out and calculate what the number it converges to. If it converges, my sum is going to be equal to whatever, bless you, the first term is divided by 1 minus the ratio. This is really one of the only infinite series that I will actually be able to figure out what it sums to. The rest of them, it goes past what we can actually figure out. But geometric series, we can go, oh yeah, this sums to this number right here, a 7, or a 5, or something like that. If the absolute value of the ratio is greater than or equal to 1, that's going to diverge. So, there is your first tool in your toolbox. It is the geometric series test. By the end of this week, we're going to have 3 more. We're going to have 4 total. You're going to have 8 in total once we end next week, where you're going to have to look at series and identify them and say, great, that looks like a geometric series. Let me use this test. Or this is going to be a ratio test. Or this is going to be a limit comparison test. You're going to have a bunch of tests that you're going to have to be able to go through, identify, and use.
What's that sign right there?
Which one? This one?
The sign between the one.
This is a greater than.
Oh, that's absolute.
This absolute value.
We're not so bad.
All right, let's do some quick examples of this. Example number 1. Now, luckily for you right now, we literally only know one series. So I can only throw one type of series at you. Obviously, everything I'm going to throw at you is going to be a geometric series. Let's go. 1/2 raised to the n exponent. Very planned out. This is the one we looked at the beginning. This is the very first infinite series we looked at, where that square, where I was filling in halves and halves and halves. You already know that in your brain, based off of what I told you, what should it equal? 1. Okay, let's prove and see if all of this connects together. It's a geometric series because it's a ratio raised to an exponent power, a constant raised to an exponent. Is it going to converge or diverge? Converge. That's the actual question I'm answering. And all of these, I'm just trying to see if they converge or diverge. With all of these, and you never have to ask, with all of these, you always have to justify. But luckily for you, we have a nice little package that we can just tie a bow on it and say, boom, this is it. So the way we justify these is by naming the test that you used. What test did we just use and go through our head? Right, so we say this converges by the geometric series test. You don't have to state anything about the ratio. You don't have to do anything. I and the AP graders will know that if you're saying by the geometric series test, that's a nice package that if you open up the box says, the ratio is this, boom, boom, boom. That's your justification. Cool?
I don't understand how to use the test.
You look at the ratio right here, the number underneath the exponent. You see if it's less than 1 or bigger than 1. If it's less than 1, it converges. If it's bigger than 1, it diverges. So this number right here, 1/2, bigger than 1?
Only with exponential.
Yes. Anything that is a number raised to an exponent. So, this one converges. I can figure out what it converges to using this equation. We did it like pictorially. We don't know if this is actually true. I could just be BSing you and say, here's this random equation. No, I'm going to prove it, yeah. The first term, if I added this up, would be 1/2 plus 1/4 plus 1/8, all of that jazz. So I'm thinking that if this sums up, it will be equal to 1/2 is the first term, divided by 1 minus the ratio. What is the ratio in this case? 1/2. So 1 minus 1/2 is 1/2. 1/2 over 1/2 is equal to 1. And that definitely goes along with what we thought at the beginning. 1 times 1 of that block, if I added up halves, would equal 1. I did not. I'm glad I did not hear it. Let's do another one. Sum 0 to infinity. I hate it. Let's go 6 4/3 to the n. It's a constant raised to a variable. What type of series would that be? It's not a divergent. It is a diverging series, but that's not what type it is. It is a geometric series. The ratio in this case is 4/3. 4/3 is bigger than 1. Therefore, this is diverging. Yep. By the geometric Everyone with it? Cool. I have some I want you to try on your own. Forewarning, I'll be using a textbook a little bit more frequently because the textbook has nice examples and nowhere else in the world are there a ton of these. So, try these. Those 6. I want you to tell me if they converge or diverge. And if they converge, I want you to tell me what they converge to. I want you to tell me what they actually sum up to. If I were you, I would be very careful with letter E, letter F. You never have to ask that question.
Okay, because we always should.
Right.